Hi everyone, my name is Gonçalo and I'm presenting Back to the Future, reverse designing a shelter for extreme weather in Antarctica. Over the past decades, the impacts of climate change and extreme weather events has been responsible for 90% of the total displacement around the world. Such events, coupled with wars and social unrest, are resulting in people losing their homes at an unprecedented and growing rate, forcing them to rely on semi-permanent structures. To explore the design of these structures in extreme cold and winds, a prototype tent was made and tested on a site at Collins Bay in King George Island, Antarctica. During the 12 months of testing, some damage was recorded resulting from high levels of humidity in the structure and wind damage impacting the outermost fabric layer. This research attempts to reverse design the tent comparing theoretical and field data. With algorithmic design, the shelter was modeled within the site environment and comfort and airflow simulations were made. Durability and comfort performance are discussed and compared with permanent standard structures, as well as their implications and liability for the design in unpredictable future climates. To achieve these goals, the team retrieved weather data from the local authorities on site, which included the yearly values of wind speed and direction. Additionally, within the shelter, the team collected data from data loggers comprising indoor, outdoor, and dew point temperatures and relative humidity. The parametric model was created so that the parameters that may vary are the trellis bottom and top radius, number of beams and their shifting, and the width and length of the beam section. In this case, the parameters were chosen so that the shelter fits its original shape. Then, the model is automatically exported in the required geometric format for each simulation. In this case, for the airflow simulation we used OpenFOAM with Butterfly to simulate outdoor airflow using the specified inputs. We tested the most extreme case in each month since last year's expedition, which was 70 knots from the east. Moreover, we tested the main wind directions during that year with the maximum speed value. For the comfort analysis we used Energy Plus with Honeybee, and the shelter geometry, its material properties, and weather data gathered by the data loggers as inputs. Lighting and occupancy schedules were switched off due to the existing conditions of this shelter. The lodge was deployed in Collins Bay between the refuge base and a rocky slope, which creates constricted sections and makes it prone to higher wind speeds and the appearance of vortex. The fabric ribs were numbered and mapped through their position and height to include them in a model of the shelter at Collins Bay area. 3 simulated wind tunnel tests with a 45-second direction were made comprising the northern, eastern, and western directions. In the northern wind tunnel test, speeds over 23 knots are registered in the eastern side of the structure and around 12 knots in the western side. Regarding the eastern wind tunnel, maximum velocities were reached in the northern and southern side of the shelter, while the western wind analysis showed high speeds hitting the southern area rock protection, which may have prevented bigger damage. Results from the northern and eastern wind analyses showed higher values in the damaged areas due to the constrictions created by the shelter's cylindrical geometry, the terrain near the eastern side, and the permanent refuge in Collins Bay on the western side. Moreover, the speed heat and vector maps show a clear relation of high speeds and constricted areas with damaged zones in the structure. The observed results, besides yielding valuable insight about the location of the damage reported, can help with the prevention and protection of high-risk structure areas, as well as help develop solutions for emergency displacement situations. For the shelter's comfort performance and comparison, upon arrival at Collins Glacier, loggers were set from February 2nd to 9th. The team occupied it for repairs and surveys from the 5th in the afternoon to the 8th in the morning. Comparing the indoor and outdoor temperatures, the tent performed well during occupancy schedules, showing a good capacity to retain heat both from the human body and the gas heater used, showing a maximum of 27 degrees. However, during 1 a.m. of February 5th and 9th, the temperature reached low negative values, easily countered with enough clothing layers. Additionally, High levels of humidity are seen, which may have contributed to the humidity damage suffered. Results for the simulated shelter compared with the recorded ones show the biggest discrepancies during the occupancy period of the shelter, since the respective schedules were turned off during the simulation. If we consider this period, it is visible an average deviation between logged temperatures in the field and those simulated of more or less 2 degrees Celsius, and with the maximum values reaching a standard deviation of 10 degrees. However, if we exclude the occupied period, this lowers considerably to a standard of 5.5 degrees. When comparing the shelter's simulated annual indoor temperatures with that of a permanent structure with standard-grade materials, the latter shows less thermal amplitude. From the heat map presented, during summer, the shelter's temperature reaches averages of 4 degrees during the night and 14 degrees during the afternoon. However, during hard winter, it shows an inability to sustain human life without extra support, with temperatures reaching -14 degrees. This is where the standard structure proves itself to be more efficient, since it's visible a smaller thermal amplitude with minimum values of -2 degrees and maximums of 5 degrees. In conclusion, about the tent performance, results show good thermal heat storage during the day, and however, minimum negative temperatures similar to outdoors were registered. Additionally, the high humidity values and the damage registered are an indication that the shelter is not doing well regarding infiltrations. Finally, from the yearly analysis and comparison, results confirm that despite the shelter adequacy for summer expeditions, it is still a long way from being able to support life during winter. Regarding the methodology of this research, the expedition proved valuable to retrieve reliable data and compare it with a reverse design building with integrated algorithmic process. This yielded trustworthy results regarding building performance simulations that may be helpful for further improvements, or even further designs and projects. However, high discrepancies are visible due to the schedules of occupancy being off and material properties divergence. Future work on this topic is going to be conducted around the exploration of design parameters and its integration with structural analysis and optimization. This can be done through analysis of wind load's impact on the structure, and with the results, it is possible to apply a multi-objective optimization approach to minimize the shelter deformation and minimize its costs according to the materials and defined design parameters. We are convinced that this can prove helpful in the creation of adaptive solutions capable of responding to the rising challenges from this decade. Thank you all for watching. Have a nice day.